10.3 notes, polar coordinates, page 5. And so now we want to take a look at how to graph something in polar form. We're going to do more of that next section, and we're going to get definitely into some of the more complicated polar graphs. But let's take a look at this one real quick. R equals 2 secant theta. First thing I want to do is see if I can rewrite this to something I'm a little more comfortable with. So R equals 2, secant is 1 over cosine, so 2 over cosine theta. I'm a little more comfortable cranking out cosine values than secant, so that's what I'm going to go with. Let's see how we can do this here. I am going to plug in a value for theta. I want to crank out a value for R and see if I can figure out what this graph looks like on the polar grid before I rewrite this in rectangular, because I'm much more comfortable graphing in rectangular. So first things first, I'm going to plug in theta equals 0. At 0, the cosine is 1, so 2 over 1 is 2. Easy enough. I don't really want to deal with cosine being square root of 3 over 2, so I'm going to avoid my pi over 6's. But at pi over 3, cosine is 1/2. 2 over 1/2 is 4. So that's doable. Pi over 2, that's going to be undefined. I'm not even going to touch that at this point. Let's go 2 pi over 3, where my cosine is negative 1/2. That makes my R negative 4. At pi, my cosine at pi is negative 1, so I got 2 over negative 1. That makes that a negative 2. I could continue 4 pi over 3. Cosine there is negative 1/2, so it's negative 4 again. And at 5 pi over 3, my cosine is positive 1/2, so I got a 4. And then at 2 pi, it's back to 0. I get 2. So let's see if I can plot these points. So when I've got 0 degrees, I am at R equals 2. At pi over 3, I am at 1, 2, 3, 4. At 2 pi over 3, let's see if I can, 2 pi, super big. Don't need anything that fat. 2 pi over 3, so I'm right here. My negative side would go that way. So at 2 pi over 3, I'm at negative 1, 2, 3, 4 right there. At pi going this way, I'm at negative 2, so that hits this point again. At 4 pi over 3, down this way. Where's my 4 pi over 3? Right here. That's the same line as pi over 3, so I've got negative 4, which hits at this point again, and at 5 pi over 3, I'm at positive 4 here, and then at 2 pi, all the way around and back at 2. So this, hitting these points, theoretically is the straight line that goes through those points. Let's see if I can get a little better at this. Good enough. Oh. Okay. So straight over, that's 2. If I were plotting this on a rectangular coordinate grid, let's see what we got here. So this, I'm going to multiply both sides by cosine of theta, because I know that R cosine theta equals x. And so now I get this, x equals 2, which is this line right here. So, moral of the story, they both look exactly the same. Definitely easier to graph this in rectangular coordinates, whereas on that last one, that equation of the circle was easier to graph in polar. So, nice to be flexible and be able to go both ways. Example 10, we want to rewrite this polar equation, r equals 4 divided by sine theta plus 7 cosine theta, to a Cartesian. So write in the standard form of a conic if possible and identify the conic sections. So hopefully you remember your conic sections: circles, ellipses, parabolas, and hyperbolas, because you are going to need to be able to recall those equations. First thing I'm going to do here, though, is multiply both sides by that sine theta plus 7 cosine theta. I definitely want to get that out of the denominator. That gives me r sine theta plus 7r cosine theta, which is y plus 7x equals 4. Y equals negative 7x plus 4, and this is the equation of a line. There's the standard form of a line in that y equals mx plus b form.